Hello everyone, my name is Vincenzo Pecunia, hailing from Soochow University. I am very pleased to present at FLAPS 2020, so I would like to thank the organizers for this great opportunity. Today I will share with you about the exciting results in low voltage, low power TFT electronics that we have obtained by using carbon nanotubes and hybrid nanodielectrics. Before I start on that, please allow me to share a word on where we're based. My group is at the Institute of Functional Nanosoft Materials of Soochow University, which is located in Soochow, China. And we are a multidisciplinary team researching in large area optoelectronics based on emerging solution process semiconductors. Without further ado, here's the outline of my talk. I will firstly make the case for easy-to-fabricate, low-voltage, complementary or complementary-like TFT electronics. After that, I will share our exciting results on Ambipolar complementary-like TFT electronics, which combines printed carbon nanotubes and hybrid nanodielectrics. Building on the newly established paradigm of deep-subthreshold ambipolar operation, I will show that this TFT electronics can operate at record low supply voltages and power dissipation. Additionally, I'll show its application to self-powered TFT electronics. Finally, I will discuss the significance and implications of this work. Now then, the case for easy-to-fabricate, low-voltage complementary or complementary-like TFT electronics. The development of low-voltage TFT electronics is directly relevant to manifold applications that require compact, flexible, low-cost and portable devices. These devices are needed in order to fully realize the sensorization revolution currently underway. For instance, this involves place and forget smart sensor systems, smart homes, Internet of Things devices, etc. In many such cases, TFT electronics will need to operate with a small supply voltage, often less or much less than 1 volt, and the small power available, for instance, from compact energy harvesters, which could be photovoltaic cells, thermoelectric generators, RF energy harvesters, etc. What is then to be regarded as the ideal TFT technology that could meet this demand for low-voltage TFT electronics? Two attributes are essential: complementary and easy to fabricate. Of course, complementarity has long been regarded as key to facile circuit integration and robust noise immunity, in fact well before the advent of TFT technologies. So I will need to spend many words to convince you about the importance of a complementary approach. However, I would like to stress the importance of ease of fabrication. In fact, a technology with minimal complexity is essential in order to ensure a high fabrication yield and low cost. The complexity of a technology firstly takes the form of material complexity, which relates to the fact that every single material that needs to be deposited and patterned requires robust control of its electronic properties. In a TFT technology, complementary circuits would generally require 2 semiconductors, 2 different dopants, 2 sets of source and drain metals, 2 surface treatments for source and drain electrodes to optimize charge injection, and perhaps 2 encapsulants. That's a good number of materials, isn't it? Additionally, higher material complexity directly results in higher process complexity. This is due to the need, first of all, of adding 1 extra step to the fabrication process for each additional material in the device stack, but also due to the considerable alignment overhead that comes with it. In turn, this entails a higher integration complexity, which refers to the need of compensating at a circuit design level for the mismatch in the device characteristics associated with the many materials used. In order to ensure ease of fabrication, finally, solution-based additive methods are to be preferred, as they considerably simplify and streamline the fabrication process. Organic semiconductors, carbon nanotube networks, and metal oxide semiconductors have been explored in recent years for low-voltage TFT electronics. Organic semiconductors generally offer much better performance in p-channel TFTs. Nonetheless, impressive demonstrations of low-voltage complementary circuits have been produced to date, but they rely on vacuum-based deposition methods. If solution-based methods are used instead, bulk trapping and disorder effects generally hamper low-voltage complementary integration. While CNT-TFTs have generally enabled complementary low-voltage circuits, such circuits, however, are quite demanding in terms of material and process complexity, for instance, due to their use of different dopants, different source and drain metals, different encapsulants, etc. Finally, metal oxides enable excellent TFTs to be made with N-channel character, while their P-channel counterparts have been lagging far behind. Therefore, a straightforward route to complementary metal oxide electronics is still being developed. All of this leaves us to wonder, how can we realize easy-to-fabricate and complementary-like low-voltage TFT electronics? Against this backdrop, let me then share how we have approached the goal of realizing low-voltage, easy-to-fabricate, complementary-like TFT electronics. In order to realize low-voltage printed CNT-TFTs, we firstly considered boosting the gate channel coupling through an easy-to-fabricate hybrid nanodielectric based on the phosphonic acid molecule shown here. Additionally, in order to preserve the ambipolar properties of CNTs, we sought to minimize the doping affected by ambient species. Therefore, we coated our TFTs with a polymer-thin film. As you can see from the TFT characteristics shown here, a CNT-TFT without this coating would gradually lose its ambipolar character. By contrast, the TFT characteristics with the sample coated with the polymer film will still present its inherent ambipolar behavior. Importantly, this approach only features one semiconductor, one source drain metal, and no dopants. Therefore, it is characterized by minimal material complexity. The transfer characteristics of the resultant TFTs show clear, well-balanced ambipolar behavior at low voltage and with good uniformity. In fact, these transistors give balanced and comparatively steep subthreshold slopes, particularly symmetric electron hole mobility values, and particularly symmetric threshold voltage values for both electron hole channel conduction. The balanced capability of our TFTs to conduct electrons and holes is also confirmed by their output characteristics shown here over a voltage range of plus or minus 2 volts. By integrating such ambipolar transistors in CMOS-like fashion, as shown in the micrograph, we could obtain, for instance, complementary-like inverters. Their voltage transfer characteristics give a fairly symmetric switching threshold, and their high-to-low transitions cover a large fraction of the rail-to-rail range, especially at low VDD values. For those of you that wonder about the hysteresis that appears in these characteristics, we found that it arises from trapping due to impurities in the CNT ink, an issue that we later solved. These inverters also give a very large voltage gain, up to about 90 for VDD equals 2 volts. All of this provides the first ever demonstration of the viability of ambipolar, complementary-like, low-voltage CNT-TFT electronics through hybrid nanodielectrics. Now I'd like to move on to discuss how we've taken this work further and realized ultra-low-voltage, ultra-low-power TFT electronics. In order to use energy harvested from the environment to power it, TFT electronics should preferably operate at ultra-low voltage, that is VDD less than equal to 0.5 volts, and ultra-low power, that is less than 1 nanowatt per gate. Recently, there have been impressive demonstrations of ultra-low voltage, ultra-low power TFT electronics, but they either relied on a unipolar technology as shown here, or on a complementary technology requiring significant material complexity. All of this is not consistent, of course, with the ideal of easy-to-fabricate and complementary TFT electronics that we expressed at the beginning of this talk. Additionally, ambipolar TFTs have been generally regarded as inherently leading to circuits with high power dissipation, due to the fact that their channel is always an accumulation of either holes or electrons, as shown here. When working on this, we ask ourselves, could our approach to low-voltage CNT-TFT electronics cope with ultra-low VDD values? Here's what we obtain from the input-output characteristics of one of those inverters when using a power supply voltage of 0.5 volts. Not too bad, right? But then, when we reduced the VDD to 0.4 volts, the issues with these inverters became apparent. In fact, while the noise margins for VDD equals 0.5 volts are still okay, at VDD equals 0.4 volts, we don't really have noise margins anymore. How could we then address this issue and make our ambipolar carbon nanotube TFT circuits work at lower VDD values? We then thought that if we could somehow rigidly shift our ambipolar TFT characteristics to the right, so to speak, then we should be able to obtain a more balanced ambipolar CNT-TFT input-output inverter characteristic as shown here. We then thought that based on a more symmetric inverter input-output characteristic that would follow from the rigid shift, we could then reduce the power supply voltage further down without compromising the noise margins, and therefore we would be able to operate our inverters at ultra-low power supply values. The rigid shift of the ambipolar CNT-TFT characteristics that we were after was in fact equivalent to a shift of the flatband voltage of our transistors. This is evident if we look at the energy band diagrams shown here, which depict the source and drain electrodes as well as the semiconductor channel. In A, the gate voltage is greater than the flatband voltage. Therefore, the injection barrier between source drain and the semiconductor will be thinned and electrons will be let in. Symmetric considerations hold for the situation depicted in B, which corresponds to hole injection. For the CNT transistors we have considered up to this point, there is an electron current injected for Vg equals 0 volts, which means that we are in the situation depicted in C with the energy bands of the semiconductor corresponding to the ones shown in gray. But if we could somehow shift the flatband voltage by an amount in the 0.1 volt range, at Vg equals 0 volts, the energy bands of the semiconductor would look like the ones shown in green, and the TFT characteristics would then be centered around 0 volts as desired. In order to achieve the desired flatband voltage shift, we considered using a hybrid nanodielectric comprising a SAM molecule with dipole moment opposite to the molecule we considered earlier, as shown here. In fact, this led to a rigid shift in the transistor characteristics by an amount in the 0.1 volt range, as shown in this plot. While SAM nanodielectrics have been reported in the past with organic semiconductors, in fact, this is the first demonstration ever of their capability to deliver a controlled flatband voltage shift of CNT-TFTs. Additionally, we were able to demonstrate through scanning Kelvin probe microscopy that this shift directly arises from the dipole moments of the SAMs we employed. In order to appreciate the significance of these findings with CNT-TFTs, I'd like to briefly discuss the two closest relevant prior reports on CNT-TFTs comprising hybrid dielectric stacks. In this first report from the Bowes group, different hybrid nanodielectrics resulted in p-channel only TFTs instead of ambipolar TFTs as in our case. This study did report differences in the threshold voltage of TFTs with different SAMs, but these differences and their spread are so large to the point that the authors could not conclude on the origin of such shift. Importantly, these shifts are dramatically different from the control shift in the 0.1 volt range that we observed. The only other relevant work is from the Zamsel group. In this study, they tested a number of hybrid nanodielectrics comprising different SAM molecules. Also in this case, the resulting transistors were p-channel only, and additionally presented very large hysteresis, as you can see from these plots. In fact, such hysteresis prevented any assessment of the trend in threshold voltage shift versus dipole moment of the SAMs. All of this indicates that the control shift we have achieved with our ambipolar CNT-TFTs and our ability to directly link it to the SAM dipole moments is a first for CNT-TFTs. Going back to our deep subthreshold ambipolar inverters, the flatband voltage shift achieved with the fluorinated SAM molecule did have the desired outcome. Inverters did acquire a more symmetric characteristic, and this was thanks to their more balanced ambipolarity, which in fact does not only involve their flatband voltage, but also their mobility and subthreshold slope. And this enabled, firstly, much larger noise margins at VDD equals 0.5 volts, as you can see from the plot here. Balanced ambipolarity, that is symmetric subthreshold slope and mobility and flatband voltage around 0, then enabled us to establish the paradigm of ambipolar deep subthreshold TFT electronics. Complementary-like digital gate characteristics were obtained down to a power supply voltage of 0.2 volts and with a power dissipation in the range of femtowatt per micron channel width. Importantly, this was achieved with minimal material complexity, considering we only had one semiconductor, one set of source drain metals, and no dopants. This power supply voltage and power dissipation figures are record-breaking for circuits of comparable minimal complexity, as shown in this diagram that graphically presents the power consumption supply voltage for all relevant TFT technologies, including organic and metal oxide. Now I'd like to show you how we built on these results to demonstrate self-powered CNT-TFT electronics. In order to explore the relevance of our ambipolar deep subthreshold electronics to real-world applications, we have assessed its performance when powered by an environmentally friendly lead-free perovskite cell placed under indoor light. As you can see from these plots here, our inverters can still function while being powered by the indoor photovoltaic cell, also giving gain values around 10 volt per volt. Considering the power dissipation of our gates, a millimeter-scale green indoor PV cell could power circuits equivalent to 10,000 NAND gates, a level of circuit complexity absolutely relevant to real-world applications. Therefore, our ambipolar deep subthreshold approach offers a concrete opportunity for self-powered TFT electronics. After showing you our demonstration of self-powered CNT-TFT electronics, I'd like to discuss now the conclusions and outlook of this work. In this presentation, I've shown you the first ever demonstration of low-voltage CNT-TFT electronics based on hybrid nanodielectrics. Additionally, I showed you that well-balanced ambipolarity through the fine-tuning of the flatband voltage enables ambipolar deep subthreshold electronics. which delivers complementary-like operation with minimal material complexity, a record low supply voltage and power dissipation. Finally, I've shown that our approach can deliver self-powered electronics in combination with emerging green indoor photovoltaics, which is highly attractive for application areas such as smart sensor systems and wearable electronics. Finally, I'd like to thank my group members that have contributed to this work, the funding bodies that have supported us, and our very helpful collaborators from all around the world. And of course, thank you all very much for your attention.